Keep this.
Take the place here. Multi-scale feature fusion with adaptive attention to robust image deblurring.
Thank you, Chair. Thank you very much. I'm sorry, I have a flight to catch, so please. I have a flight to catch, so I'm really enjoying to being here. Good luck. Thank you very much. Thank you.
Hello everyone. Today I'm going to present our recent work on Robust Image Deblurring, practically multi-scale feature fusion with adaptive attention to Robust Image Deblurring. First of all, let me introduce the authors, Swaglavan and Suryavan, and I'm visiting and Mithapis Award from Brown University and Sunyoung Women's University from Bangladesh and South Korea. Image deblurring is a fundamental task in computer vision and image processing. Blurring is a common deformation caused by camera motion and objective movement of the focus or atmosphere turbulence. The goal is to recover a sharp image from its deblurred observation, which is an ill-posed inverse problem. The traditional methods require explicit modeling of the blur corner and often struggle with complex spatially varying blur patterns. Recent advances in deep learning have significantly improved deblurring performance by running end-to-end mappings from blurry to sharp images. In reality, blur is rarely uniform across images. Some regions require more sophisticated processing than others. So our insight is to adaptively allocate computational resources based on local blur characteristics and content complexity, leading to more efficient and effective deblurring. So our proposed framework is called multi-scale feature fusion with adaptive attention, called the MSFAA framework. So it consists with the main four components: context-aware feature equations called copying models, and adaptive attention fusion model, and multi-scale feature extraction backbone, and instruction model. So traditional deblurring methods fall into two main categories. One is non-blind method, and the other one is blind method. So which estimate both the kernel and the sharp image together, often relying on image priors such as sparsity or the darkest channel. While these approaches perform well for uniform blur, but they can struggle with spatially varying blur patterns and may be computationally intensive. So recent advances in deblurring leverage in CNN for end-to-end mapping from blurry to sharp images with improvements such as multi-scale architecture, called residual learning, and recurrent structure for better performance. Attentive models have also been introduced to help models focus on the most useful image information. However, these approaches often process the entire picture map uniformly, which can waste the system. So most existing deep learning approaches process all image regions with the equal computational resources regardless of their blur complexity. And multi-scale feature fusion has demonstrated strong effectiveness in computer vision tasks such as image restoration, as it enables models to capture and integrate information at multiple stages for better results. However, these approaches typically rely on fixed fusion strategies that do not adapt to local image context, potentially limiting their ability to fully explore region-specific information. So this lack of adaptability may hinder performance in scenarios requiring nuance and context-aware feature integration. So our MSFA framework processes the input block image through the multiple stages using a shared wave encoder. Given a blurred image input, and we create a pyramid of images at different scales by downsampling. So the copy model generates importance maps for features at each scale, which guide the adaptive attention fusion process. And the fused features are then processed by the reconstruction model to generate the final deblurred image. This allows us to capture information at different resolutions and handle blur at varying degrees. So this is our formulation that the image deblurring problem can be formulated as the screen. The B means is the blurred image, and I is a sharp image, and the K is a broken, and X it denotes the convolutional operation, and the M represents the noise. Our goal is to recover the sharp image I from the blurred image B without explicit knowledge from the blocker K. So the purpose LSFA formula consists with four main components, as I said before, to effectively have the blur at one scale, and we extract features from the input image at multiple resolutions. So given a blurred image input B, and we create a parent images such as B1, B2, and B3. So where BS is obtained by downsampling B by a vector of S. So each image in pyramid is processed by a shared weight encoder E to extract features, where the Fs represents the extracted features at scale S. And the encoder E consists of a series of residual blocks with deleted convolutions to increase the receptive field without increasing computational complexity. So the context-aware feature importance model called copy model is designed to access the importance of features at each scale based on local block characteristics and content complexity. For each scale S, the model generates an importance map NS that highlights the region requiring more sophisticated processing, shown on the bottom of the screen. So C represents a lightweight convolutional network, and sigma is a sigmoid activation function. So the importance model MS has values in the range of 0 to 1, and with higher values indicating regions requiring more attention. So the copy model is shows the importance of features at each console, and based on local block characteristics and content complexity. It generates an importance map for each scale and highlighting the regions. The copy model has two main components, which is blur detection blur and content complexity estimator. The adaptive attention fusion model combines features from different scales based on their estimated importance, and features from lower scales are upsampled to match the highest resolution, then weighted by their importance maps and fused. This allows the network to emphasize features from most relevant scales for each spatial location, leading to more effective deblurring. The fused features are processed by a reconstruction model to generate the final deblurred image. And we also implemented a progressive refining strategies, where the network is applied in a coarse-to-fine manner. And each stage, the network processes the blurred image along the previous prediction and focuses on recovering increasingly finer details and maintaining global consistency. Our network is trained using a combination of pixel-wise perceptual and adversarial losses. So lambda 1, 2, 3 are weighting methods, and the pixel-wise loss includes L and SSIM losses. The perceptual loss measures the difference between feature representations of the ground truth and predicted images using a pre-trained BGG network. The adversarial loss encourages the network to generate realistic sharp images. So we validated our approaches on standard deblur datasets with the GoPro dataset and the real blur dataset. And our network is implemented in PyTorch and trained on NVIDIA RTX 3090 GPUs. We use the Adam optimizer with initial learning rate of 1e-4 iterations and trained for 600,000 iterations. So data augmentation techniques such as render, cropping, flipping, and rotation and applied for the better generalization. And our MSFAA framework achieves state-of-art performance on both GoPro and real-world data sets. And on GoPro, we achieved a PSNR of 33.82 and SSIM of 0.965. And real-world, we achieved PSNR of 34.95 and SSIM of 0.951. These results significantly outperform previous methods. So we conducted an evaluation study to evaluate effectiveness of each component. The baseline model with a copy model or adaptive fusion achieves a PSNR of 32.45 and SSIM of 0.956. So adding the copy model improves PSNR by 0.65 and including adaptive attention fusion further enhances performance. The full MSFAA framework with progressive refinement achieves the best results. The visual comparison show that our method produces more sharp images with better preserved fine details and fewer artifacts compared to other methods. Our approach excels at handling complex blur patterns and recovering textures in challenging regions. And our method is computationally efficient. It achieved a good balance between performance and efficiency and outperforming other methods in both metrics. So in conclusion, our MSFAA framework introduces a novel adaptive attention mechanism for image deblurring and dynamically allocating computational resources based on local blur characteristics. Unlike prior models, our copy model dramatically allocates resources based on local blur and enhancing efficiency and visual quality. Furthermore, our lightweight design achieves faster inference with fewer parameters, making it a more efficient alternative for real-world applications. So our proposed novel multi-state vision fusion with adaptive attention for the MSFA framework for image deblurring introduces a context-aware feature importance for the copy model that dynamically assesses the relevance of features at different scales. So for the future work, we are going to plan explore the applications of our framework to add other image restoration tasks and further optimize the network architecture for real-time applications. And thank you for your attention, and we are waiting for further opportunities. And SWAT and Surin are very dedicated researchers, and me Kyung-suk Kim is down in fintech startup in Korea, but I'm willing to be in the research together. So if you have any questions, please feel free. Thank you.
Thank you. Thank you very much for your presentation. It is very interesting. Do you have questions?
Thank you very much.
Yes.
So thank you for your presentation, but I would like to know about that you have considered local blurriness and global both, or just only local?
We just focus on local in this study, but we are going to research more if we can adapt more alternative models in this as a further research.
Mm-hmm. And also I can see that the frames per second is like 19, if I remember correctly. But nowadays more application or more models are developing for the real-time application. So how you think about your model like that? For example, some applications are like 2-3 millisecond requirements. So how your model will work on that?
So we focused on to make the model as a right-way model. So we focused on the efficiency of the as you
showed us that when you compare to other methods, your model is better. But you are not sure, we are not certain that there is another method better than yours. Correct?
Maybe.
He has a better method than you.
Yes, so there might be another one better than yours. And what I think is very important to include is to analyze how your method is improving the blurring process when it is better or worse in to find properties, to find the full analysis based on theory approach or based on some special procedure prepared images, and to check when your method is going in the better position or in the wrong position. Because when you just check the statistical analysis that you did, it is just we got some examples, but you don't know exactly how your method is working. That's true?
So you mean that I don't know about the...
Because you don't know when your method will be give better results, when your method give
I think it is comment, not questions.
so there is a question about if you just did some analysis, more deeper analysis than only statistical analysis.
Oh yeah, but as you saw that I saw the statistical tables on the presentation because we were researchers from another countries, so we could communicate with just the table and the numbering statistics. So yeah, that could be an improvement as you told about.
Because really I'm not convinced if your method is so good. Because this is only just example of that your method is give some better result than others, but still I'm not sure when your method is working better than others in such a case.
But your analysis maybe requires a huge material that is not proper for conference paper.
Okay, I'm just asking about what is going on in your more study that you needed.
Yes.
For me, it's enough that you just explained that more study is needed to check if the method is really better than others, because this is not enough at this moment. Yeah, I agree.
In my opinion, your mind is right, but for sometimes full paper, full journal paper
Exactly.
in this topic.
Okay, thank you very much. Thank you.